Okay, so this is the third time I've tried to record this, and I've had technical problems, so forgive me if I'm being a little short here. Okay, so I wanted to go over just the couple of problems that you had for homework, and then also do one more example for today. And tomorrow in class, we'll do some more. So I asked you to do 12 and 13, and 12, you're adding all the positive integers starting with number 3. 3 plus 4 plus 5 plus 6 plus 7 plus 8. And this statement is saying that if you do that, it'll equal n times n plus 5 divided by 2. So n is how many numbers you're actually adding. So 3 plus 4 plus 5 plus 6 plus 7 plus 8, there are 6 numbers here. So in this case, n would be 6. And prove that it is true for all possible n values. 3 steps. You have to show that it works for step 1. And step 1 means when n equals 1. Well, when n equals 1 over here, you've got 1 times 1 plus 5 divided by 2, which is 6 divided by 2, which is 3. On the left side of the equation, when n equals 1, you just have 3. So, of course, 3 equals 3. So step 1 is done. Step 2 is the easiest step, but it's totally necessary. You have to assume that it works for just an arbitrary number of terms. And we'll just call that k. Nothing special about the letter k. We'll just call it something different. So we're going to assume that this is true up to the kth term. Then if we can show that it works for the next term, the k plus 1 term, then we've done the job. Because this process means that you are showing that it works for the next one. If it works for the first 800, you can prove that it's going to work for the 801st. And because you have this method to show that it's going to work for the next one. And if the 801st one works, then you just proved it works for the next one. So the 802nd one will work, and then the 803rd, and so on and so on. So it just keeps on going forever. And you have proved that it works for all positive integers. So this is what you want to show. It's the same thing as in step 2, except k is being replaced with k plus 1. You're just going one more step further. Now start on one side of the equal sign. Here's the equal sign. Start on the left. And I rewrote that right here. I clean this up. K plus 1 plus 2 is k plus 3. And then this always happens. You always have a chunk that is your assumption. So this first chunk right here is equals to this, k times k plus 5 over 2. I assume that to be true. So I replace it with this. I add k plus 3. Now what do I do? Well, I got 2 fractions. I always have an inclination to just combine them. So let's combine these 2 fractions and see what we get. I don't know how it's going to work out at this point. So I don't want you to think that you should know. And if you do, great. But at this point, it's unclear to me personally how it's going to continue. But I see a fraction and a non-fraction. Well, I have the skills to add 2 fractions, so let's just do that and see what happens. It may work out, it may not. Well, to get these 2 things to combine, I would multiply this by 2 over 2 to get a common denominator. And then now I can distribute the 2, distribute the k, and I get this, which simplifies to this, which factors to this, which equals this. And that's exactly what I needed to show. These 2 things, this and this, are identical, so I have proven it. So it works for the next one. And since step 1 means that it works for the first one, I just showed that it works for the next one. So if the first one's true, then the second one is true. And since I proved that it works for the next one, then the third one is true, and the fourth one, and so on and so on and so on. Number 13 was a little bit more simple, I believe. You're adding the odd integers. And this is really interesting. If you add the odd integers, it equals a square. Let's just check that out. So if I take 1 plus 3 plus 5 plus 7 plus 9 plus 11, 1 plus 3 plus 5 plus 7, first of all, that's 6 numbers here. According to this, it should equal 36 because 6 squared is 36. Well, 1 plus 3 is 4. 4 plus 5 is 9. 9 plus 7 is 16. 16 plus 9 is 25, and 25 plus 11, lo and behold, it's 36. So if you've done this, what you've just shown is that it works when n is 6. But we need to show that it works for any n value, an arbitrary amount of n value. So mathematical induction, we show that it works for step 1. When n is 1, this becomes 1 squared. When n is 1, it's the first term, and the first term happens to be 1. Well, 1 does equal 1 squared, so step 1 is good. Step 2, assume it works for an indefinite amount of n values, so we just call that k, or I'm sorry, an arbitrary amount. And then let's show that it works for the next one, the k plus 1. So you go back to this step and replace k with k plus 1, like what I've shown here. So this k squared is going to become k plus 1 squared. 2k minus 1 is 2 times k plus 1 minus 1. And this is the one right before it. So I take the left side of the equation and I rewrite it. I can combine like terms. I could distribute this 2. I get 2k plus 2 minus 1, and that just simplifies to 2k plus 1. And then here it is again. This first section right here is what we assumed in step 2. So this section right here is just k squared. So it's k squared plus 2k plus 1, which is this, which factors into this, which equals k plus 1 squared, and it is shown. So it may be tempting to skip steps, but don't do it, because this is a proof. It's like a legal argument. And if the lawyer thinks the guy's innocent, he's not just going to skip to the end and say he's innocent. You have to build your case. So don't skip steps. Be articulate, follow the algebraic rules, make it obvious to the reader how it flows until you get to your final destination right here, k plus 1 squared. And that's exactly what I wanted to show. And then this example is, I'm not sure if this is, some of them are tricky, some of them are not, and it's different for all people. So let's try to do this. And you should pause the video and see if you can finish this on your own. But this is saying that 1 plus 2 plus 2 to the second plus 2 to the third all the way to 2 to the n minus 1 equals this. Well, realize this is 2 to the 0 plus 2 to the first plus 2 to the second plus 2 to the third, etc. And let's just check this out. 2 to the 0 plus 2 to the first plus 2 to the second plus 2 to the third plus 2 to the fourth plus 2 to the fifth. Let's just go the first 6 digits in. And this is 3 plus 4 is 7 plus 8 is 15 plus 16 is 31 plus 32 is 63. So that is, how many numbers did I add? 1, 2, 3, 4, 5, 6. So 2 to the 6th minus 1. Does that equal 63? Well, 2 to the 6th is 64. And 64 minus 1 does equal 63. All right, let's prove it works for all positive integers. Step 1, for the first term on the left is 1. On the right-hand side, the first term is when n equals 1. So 2 to the first minus 1 is 1. Step 2, assume that is true up to integer k. So replace all the n's with k's, and we get this statement. So we're going to assume that this is true. Step 3, show that it's true for the next term. So replacing these k's with k plus 1. And this is my goal. So I'm going to start with the left-hand side and see if I can get there. Well, okay, so what's right behind 2 to the k? What's right behind 2 to the third? 2 to the third is 2 to the second. Behind 2 to the second is 2 to the first. So the number that's right behind it is 1 power less than this. So right behind 2 to the k has got to be 2 to the k minus 1. And these first several terms, these first k terms, all the way up to 2 to the k minus 1, is in step 2. That equals 2 to the k minus 1. So I've got, this is 2 to the k minus 1 plus 2 to the k. And then now what? I mean, you have to get here, but how do you get there? Well, it makes sense. We may not know why, but we don't know why, how this will help us, but we've got 2 to the k here and 2 to the k here. Let's just get those two guys closer together. And then realize these two terms both have a 2 to the k in common. Actually, even simpler, they're both like terms. So I can just write, I've got literally 2 to the k's. So I can write it as 2 to the k. But I did it a different way. But the reason why you can combine like terms is because of this. These both have a 2 to the k in common. So if you factor out 2 to the k, you're left with 1 here plus 1 here. And 1 plus 1 is 2. So that's how we get that. Now, how do you get from here to here? How do you get from here to here? This is just multiplying, or you're multiplying two things that have the same base, so you add the exponents. I'm pretty confident no one would have a problem with saying that this is x to the 12th. But in my experience, students just fall off the planet when they're faced with, instead of an x, they have a number 2. A lot of students want to write down 4 to the k plus 1, but that's not true. I appreciate you want to multiply, but realize that when you're adding the exponents, you are multiplying. Like this is x to the third, that means x times x times x. If we make it x to the 12th, you're just multiplying x 9 more times. Or think about it this way. You didn't write x squared to the 12th, did you? X to the third times x to the ninth is simply x to the 12th. It's not x squared to the 12th. So we shouldn't write this as 4 to the k plus 1. It's just 2 to the k plus 1. I've got 1, 2 right here, and I've got k2s right here. So altogether, I've got k plus 1 2s that I'm multiplying. And we'll see you tomorrow, and we'll do some more examples that get a little bit more complicated.